Professor Wang from China, National University of Defense Technology, China, Changsha. The report is titled Aerosol Assisted Atmospheric Pressure Plasma Deposition for Silver Containing Antibacterial Coatings. Where is presentation? Okay, IMC. Dr. Wang, do you hear me?
Yeah, I can hear you. Thanks. Yeah,
it's excellent. I'm. You have more time for your presentation. You have 30 minutes for report and 5 minutes for question. Okay.
Okay. Okay. Thank you.
Okay. So let's begin, please.
Thanks for your introduction. Hello, everyone. I'm Lei Wang from China. My previous affiliation was in Ginton University, and most work was done there. So here I want to introduce my work during my stay in Ginton University. It's about aerosol-assisted atmospheric pressure plasma deposition for silver containing antibacterial coatings. In this talk, first I will briefly introduce antibacterial coatings. Secondly, I will share how aerosol-assisted atmospheric pressure plasma deposition was performed and the analysis were carried out for the deposited coatings. And thirdly, we will characterize the coatings on the surface morphology and chemical composition. And fourthly, we'll check the antibacterial effects and the cytotoxicity of coatings. And finally, the main conclusions will be given. Antibacterial coatings are functional coatings which can inhibit the growth of microorganisms or materials. Antibacterial coatings have many applications, such as medicine or healthcare, textiles, for the package, indoor air quality. According to the market report, antibacterial coatings contributed to more than $100 million in the global market of last year, especially as we experienced the COVID-19, and there's a huge requirement for the antibacterial coatings and also antivirus coatings. Regarding the medical applications of antibacterial coatings, we can find some examples like wooden dressings, implants, and catheters. A typical example of antibacterial coatings is silver-containing antibacterial coating, which has been widely used due to the low antimicrobial resistance. However, it may have side effects of cytotoxicity due to overdosage. Therefore, controlled release of silver ions are necessary for biocompatible coatings, especially the combination of initial burst release and followed slow release, which can be beneficial for the medical applications. When antibacterial protection in the early stage is required, and the long-term slow release is needed to prolong the lifetime of antibacterial coatings. There are many ways to produce silver-containing coatings. Traditional chemical methods can produce desired coatings. However, it has disadvantages like high cost, hazardous chemicals, tedious multi-steps. Plasma-based method shows advantages over chemical methods by overcoming these drawbacks, like simple preparation, extraordinary versatility, economical, and solvent-free deposition. Here, I would like to introduce the aerosol-assisted atmospheric pressure plasma deposition. In this talk, I will simply call this AAPPD. This technique can can deposit volatile or non-volatile precursor while preserving the molecules of precursor in the aerosols from destruction in the discharge. This technique paved the way to produce various functional coatings with core shell structure. In this work, we are going to apply this technique to synthesize several containing antibacterial coatings, which hasn't been reported before. Now let's look at the experimental setup. It includes two automators to produce HMDSO and self-natural aerosol separately, as we see on the upper left figure, and all aerosols will be carried by helium gas into a DBD chamber. The discharge is driven by AC power supply at 24 kilohertz. In the beginning, we used several silicon wafers as substrates to study the influence of experimental conditions on coatings. The experimental conditions include continuous mode for sample B. As we see, the duty cycle is 100%, and pulse mode for sample E is 33% of duty cycle, and sample F with no silver nitrate in the aerosol, and a control sample G with no aerosols. The treatment time in the experiment is 10 minutes, and the silver nitrate concentration is 100 millimole per liter. After deposition on silicon substrate, the coatings were analyzed with the SAM, EDX, FTIR, XPS to study the morphology and the chemical composition. Accordingly, we optimize the experimental condition and further use the PET fabrics as substrates in the deposition for biomedical applications. We check several ion release with SAPMS, antibacterial activity with gram-negative bacteria E. coli and the gram-positive bacteria S. aureus. We also check the cytotoxicity with murine fibroblast cells. Now let's look at the same images of sample B treated under continuous mode. The left side gives the same image at 10,000 magnification, and the right side shows the image at 50,000 magnifications. We find that there are many nanocapsules or nanospheres with regular shape in the coating. We also checked the cross-section of sample B and found out that coatings consist of a layer of polymeric matrix with nanocapsules embedded inside and grafted on the coating. Now let's look at sample E treated under pulsed mode. We can notice there are many particles or many spheres with smaller irregular shape. And that's because in the off time of pulsed mode, the polymerization slows down substantially, while the flow of two aerosols remain unchanged, leading to more irregular deposition. So when we use water aerosol to replace silicon, to replace self-nitrate aerosols for sample F, the coating surface is almost uniform with slight defects. Normally, plasma polymerized HMDSO coatings are flat, and the defects can be caused by filaments forming discharge due to the presence of water aerosols into local strong fragmentation and
We do not hear. Dr. Wang? Хорошо, что он имеет на 10 минут больше. А я вообще не могу понять, а где вот A, B части есть, а CD частей рисунков я не вижу, что-то не могу понять. Наверное, они вообще не проявились, вот они снизу должны были быть. Вот. Dr. Wang, I'm see you, but don't hear.
Can you hear me again? Sorry.
Okay, we are here.
Okay, so I'm gonna share my screen again. Sorry. Where should I start again? From here? Okay.
I think several slides back.
Okay.
As
So where
I
should
remember the 6th slide, as I remember.
This one,
Yeah.
right. Okay. So here, okay, and simply we can see here the sample, the same image of sample B on the continuous mode is we see quite big nanocapsules or nanospheres in the coating with regular shapes, and we also checked the cross section of coating and found that the nanospheres were embedded in the coating or also grafted on the surface. And when we check the samples on the pulsar mode, like sample E, and we can see smaller nanospheres on the coating. Yeah, here we can see sample F on the pulsar mode, but with no silver nitrate in the coating. We only use water aerosols in the experiment, and we found that it's almost flat, but with slight defects. When we see sample G, which is deposited with only HMDSO, it's the coating surface is flat and uniform. And when we check the EDX of sample B, and we found that the coating surfaces the coating, especially when we look at the figure B, this is about the silicon map, and it's almost uniform distributed on the surface, which reveals that the aerosol is also covered by the silicon formed by the polymerized HMDSO. And when we check the EDX map of silver, and we can see the silver is scattered, distributed, which mostly the silver is mostly deposited, located in the spherical structures. The observed area also shows that 1% of silver in the coating. So when we check sample E, EDX map of silver presents a quasi-uniform silicon element distribution, and silicon and the silver element distribution has a diffuse distribution, which is quite different from sample B. And we can see also the silver content, which is almost 21%. So based on the previous results, we made hypothesized the deposition mechanism of aerosol resistant plasma deposition. In the first stage, in stage A, before the polymerization, and aerosol droplets containing silver nitrate are transported by helium gas flow into the chamber, while HMDSO aerosols evaporate completely before entering the plasma zone due to its high volatility and resulting no nanocapsules formation in the coating. In the second stage, HMDSO and the water vapor are efficiently fragmented, and the polymerization process starts on the substrate as well as on the surface of several nitrate-containing droplets. Meanwhile, several nitric aerosol droplets are continuously evaporated and transported to the substrate due to the sedimentation and diffusion. This results in the formation of nanocapsules covered by the polymeric matrix. In the third stage, the polymerization continues on the substrate and the several nitric aerosol droplet surface to embed the nanocapsules inside the coating. As the polymerization proceeds, neighboring nanocapsules now grow in size and start to connect and intersect, as also seen in some images. We use FTIR to check the functional groups in the coatings. Most coatings give similar functional groups. Only with sample E, we can see weak band from nitrate, which suggests the retention of nitrate in the nanocapsules. XPS gives more information of coating chemistry. In the table 2, we can focus on the silicon and silver. The ratio of silicon, the silver over silicon can serve as an index for relative content of silver in the coating, as we notice that the silicon is rather uniformly distributed on the surface according to EDX results. In the pulsar mode, sample E shows a higher silver content than sample B in the continuous mode due to no polymerization in the off time. In the sample FG, almost no silver is found in the coating. Since PD fabrics are widely used in the medical application, we decided to deposit coatings on PD fabrics. For further experiments, we choose pulsar mode to deposit the PD fabrics with 2 regions. The first is the high silver content for antibacterial efficiency. The second is the mild gas temperature for PD fabrics to avoid the melting problems in the deposition. Here I want to mention that due to heat accumulation, especially when we choose samples for 10 minutes, if I do the experiments on the continuous mode, I notice that the samples, some samples kind of melt. So for those reasons, I choose the continuous the pulsar mode to deposit on PD fabrics. And we vary the aerosol flow ratio to flow ratio of HMDSO and silver nitrate in the deposition to check their antibacterial effects as shown in table 3. The antibacterial effects of silver embedded coatings directly dependent on the release of silver ions. We measure the release by with SPMS. A higher amount of silver release is found on the sample FB1, as we see in the figure. Due to larger flow ratio of silver nitrate aerosols and the thinner barrier layers against the release, which is formed by HMDSO. It's necessary to mention that there's a 2-phase release kinetics for all deposited samples. A fast release of silver is observed on the first day for FB1, FB2, and FB3. Afterwards, a slow release of silver ions. The initial fast release ensures antibacterial protection in the early stage, and which is the most essential stage for infection risk. The initial burst release of silver can be attributed to silver near the surface in the coating, especially for the pulsar mode deposition. Many nanocapsules with thinner shells cannot effectively block the silver ion diffusion into an aqueous environment, while the silver embedded inside the coating and in the capsules with a cyclic shell can be the reason for the long-term slow release. The release kinetics can be further investigated by the Cosmere-Pepper's model, and we found that it's quite a key vacuum diffusion. And bacterial effects of coatings were also examined by E. coli and S. aureus. Both bacteria were incubated with different fabric samples. After 2 days, the colony forming units were counted and their local reduction were calculated. Fabrics FB1, FB2, as we see here, shows strong antibacterial properties, which related to more released silver ions, while FB3 shows a moderate antibacterial efficiency. We also noted that the E. coli shows E. coli is more sensitive to antibacterial coatings. That's because a thick shell is found for E. coli, which prevents the penetration of cell ions into the cytoplasm and cell lysis. Cytotoxicity was studied through confocal image, which, as we say here, that the live images, the number of live cells can indicate the viability of cells. As you see here, we have 5 samples. And we put all samples and we put more samples incubated with murine fibroblast cells, and there are two control samples, like we see here, A and B, and the cells incubated on the standard protocol using unexploded medium in order to follow the growth of cells, and cells incubated with untreated PET fabrics under the same condition. Figure B shows that the PET fabric itself does not influence the viability of cells. And FB1, FB2 shows that high toxicity is found to kill all cells. FB3 is the sample FB3 shows lower toxicity with still a lot of alive cells, indicating a potential of biocompatible coatings for medical applications. The results of FB4 and FB5 indicates no cytotoxicity of coatings made from HMDSO precursor and a mixture of water aerosols. So to conclude that this APBD technique can be an effective one-step method to produce several ion release controlled coatings. The morphology and the chemical composition of coatings can be tuned by adjusting experimental parameters, and control release can be achieved by varying HMDSO and several nitrate aerosol flow ratio. And bacterial coatings on PET fabrics are obtained by optimizing HMDSO and several nitrate aerosol flow ratio on the pulsar deposition. And thanks for your attention. And I'm looking forward to your comments.
Раз. Слышно меня? Thank you, Dr. Wang, for interesting report. In spite of some technical problems, it's very interesting and good, beautiful reports. Now we have some times for some questions. Have participants any questions? Okay, I want I have some questions. Dr. Wang, how long is the antibacterial effect of your coatings? How long? Days, weeks, years, maybe?
Now I can show you a slide here. We did test for. Just wait. First, we can look at the iron release curves, and we did the test for 21 days.
20 days, da? Yes.
21 days, but we didn't continue our experiment. It takes so much time, and I think it's a good idea to check how long time can the bacterial coatings gives good performance.
Oh, okay. Thank you. Have anybody questions? Once more. Okay, I have questions once more. What is the reason for the two-phase nature of the release of silver ions from your coatings?
Yeah. Wow. So maybe it's bad for me to explain with this hypothesized deposition mechanisms. We have with this technique, we can deposit a core shear structured coatings. So as I mentioned, the two-phase release kinetics, and there's a initial burst release, which we assume that the silver is quickly released from the top surface of the coating, and as you can see here, maybe do you see my cursor there? Or you can see that there are many silver particles. Especially for those near the surface, which can be easily released, and this caused the initial burst release. And for the long-term slow release, it's because the silver embedded in the deep inside the coating. For example, if we look at the figure C, and when we look at this, for example, if we look at the silver deep, very close to the surface of substrate, it's embedded very inside, so it takes more time. It's even harder for them to be released outside. So that's the reason for the long-term slow release.
Okay. Thank you very much. Please, Dr. Chepusov.
Okay, thank you for your report. And maybe I have missed the details, but what are parameters of your pulse mode? Frequency, pulse duration, and etc.
When we look at sample E, these are the experimental conditions for the pulse mode. Here, 33% of duty cycle, and the pulse here you can see the pulse cycle of 120 milliseconds.
Okay, thank you.
Any questions? I don't see any questions once more. So thanks again.
Okay, thank you, Professor.